So did you understand how we got these three answers?
Yes.
Great. So those are our answers. I just have to put a negative on them, and I'll show you why. Remember what I told you? Huh?
So I think that those powers are tricky though, because I never understood how to get power. Like I always mess up on tests. I didn't understand like what type of current would a source have. Like I was like, is it over one? Because I know everything has a resistance on a circuit, but it didn't make sense to me. So now
Don't. You're right. You're right, but don't do that on paper. Yes. In real life, everything has resistance. But when we put it on paper, we put it in ideal form. And in ideal form, it doesn't have resistance. Make some sense?
Mm-hmm.
So what happens is if we have a source in real life, this is what they'll do. This is what they'll tell you. When you look at a sheet, it'll say, oh, yeah, this is a voltage source. It has an internal resistance of like 0.5 resistance. They have a little bit. It's like generally small. Let's say it's like 0.1. On paper, you don't write it a resistor right there. You don't do that. This is what you do. You'll draw a little resistor on the top of it in series. Make some sense? Mm-hmm. And so what you've done is you've separated the source from its resistance, but on paper, it still mathematically works out the exact same. And this right here will actually represent the full source. You see what I'm saying?
Yes.
And so that's what happens there. So the way you're thinking about the fact that, yeah, it has to have resistance, that's right. However, on paper, mathematically, we look at the ideal, and the ideal is just this. And you don't want to consider the resistance, or the resistance is wrapped inside of the resistors that are around them. So that's how we look at it on paper.
There's also like percent error because it's not, not calculating that percentage that the resistance has like on paper is within 5%, right?
Yes,
I would say.
Exactly. No, you're exactly right, because everything, you can't be exact on everything. Math is exact, but science is not, and that's just how it is. So those are your answers, but these answers are all negative. Can you tell me why these answers are all negative?
Because it's producing power, not consuming it.
Good. It's delivering power, not consuming. I'm going to tell you there's a general rule. Resistors always absorb power. Always. So resistors always have positive power. Always. Generally speaking, sources, regular independent sources, almost always give power. They're almost always delivering power.
Yeah.
But it is rare when you can force a source to absorb power, and that generally happens with dependent sources. Sometimes you can force a dependent source to absorb power. But that's no good because you're going to overheat it.
Yeah.
But no, sometimes that happens. But generally speaking, that's the way it is. How do I figure out that it's negative without me knowing that? You got to look at the convention. So look at it like this. Let's take a look at this guy right here. You see how the current is flowing up through it?
Mm-hmm.
But we know passive sign convention. Passive sign convention, current's supposed to go, stop that. Current's supposed to go from plus to minus, right?
Mm-hmm.
But the source is going like that. The source is backward. So because the source is backward, that's got to be an automatic negative. That's like the math. I shouldn't say the mathematical way. That's like the pictorial representation that proves why the sources give negative power.
Okay.
And a lot of students get upset with that. They go, but the sources, do the sources, the question that students have is, do the sources act differently from passive sign convention? And the answer is no. The sources do not act differently from passive sign convention. You got to look at it like this. When you're looking at current externally, current passes up through it. That's external. So externally, it looks like a source is deviating passive sign convention. However, a lot of people don't know this, but on the inside of the source, there's a barrier. There's a barrier. Because if you were to just go inside of the source, the current should just go down, right? It should just go from the plus to the minus and everything will be good. But what that would do is that would mean that current never leaves the source. If you put a barrier inside, the only way the plus can go to the minus is if the current leaves the source and comes back through the bottom, which is exactly the reason why circuits work. Make some sense?
Mm-hmm.
So if you look at it from the outside, the current's passing up and it's violating passive sign convention. But if you look at it from the inside and consider the current actually is going from plus to minus, it's not violating passive sign convention. So it becomes a matter of perspective. From the circuit's point of view, from the outside, sources deliver power. But if you look inside of the source isn't delivering any power to itself. It's actually losing power. It's actually absorbing the power that it spit out. So it's like a really weird perspective issue, but that actually solves it and shows you mathematically why you need to put these negatives here instead of positives. Make some sense?
Okay. Yep.
Dope.
Dope. Okay, so then last question, just really quick, just so I make sure I can remember all this, right? So just for like when we're doing BC, right, A minus B is literally because over that resistor, it start stop, right? So it's going from A to B, so that means it's A minus B, right?
Yes.
Just to clarify.
Yes.
And then the negative there for like B over the 40 is because the current was leaving it. So
yes.
It's not convention. So I just want to make sure that I was making sure I got that right.
No, and you said it perfectly. These signs, the plus, the minus, the plus, and the 6 come from the direction of current.
And that 40 thing still confuses me a little bit, just because like I understand. Well, I think that's just algebra though, right?
It's just algebra, yeah. So the whole idea is I need to pick the least common denominator or the greatest common denominator. I got 40, 40, and 10. If I pick 10, it won't get rid of the 40. It'll turn into a 4 at the bottom. But if I pick 40, the 40 will cancel with this guy, and then make this guy at the top multiply by 4. Make some sense?
Oh yeah. I think I'm just having a brain fart. I don't know why. In this for a second in my head, I was thinking about multiplying the 40 by the 40. I think I'm just tired. Okay, that makes sense.
No, you're right. You're right.
That makes 100% sense. Okay.
And just to solidify,
yeah,
it cancels. To solidify what you're saying, the reason why it's start minus stop is because current's supposed to go from plus to minus, and we know when we're looking at voltages, it's always the plus term minus the minus term. That's why it's always start minus stop. Makes some sense? And so this doesn't have to do with the direction of current. This has to do with the polarity of the voltage. Makes some sense? And so that really, it's good that you were able to kind of look at it and start to see that there are two separate things happening together. Technically, they're not, because the polarity of the voltage and the direction of the current are actually completely related to each other. But mathematically, like on paper, they look like they're backwards. And that really, really tricks a lot of students. So I'm happy that you see it for what it is. And that's not good. Once you understand it, like I know that you're probably never going to mess that up again.